Alternate history is a genre of fiction where we explore what would have happened to the world had some historical event turned out differently. So for example, we might have an alternate history novel exploring what would have happened if the Allies hadn't won World War II. What we're going to do is look at a few alternate history examples where we're going to try to explore the question, what would have happened if certain groups of people in the past had used random testing in addition to whatever other kinds of testing they were doing? And we're going to sort of specifically focus on the question, would random testing have been likely to alter the outcome of some famous software bugs, or would it have not made much difference? Would it have not been a very useful technique? And so the first case study we're going to look at is the fdiv bug in Intel Pentium chips. And so in 1994, it came to the world's attention that the fdiv instruction, supported by Intel's Pentium processor, was flawed. And so fdiv is an instruction that you would use to perform floating point division. So if we're writing assembly language for a Pentium, we would issue the fdiv instruction with two operands. And what it would do is compute the quotient of a divided by b. And so what happened is there was a bug in fdiv. And what had happened was the implementation of fdiv, that is to say the hardware implementation of this machine instruction, was intended to be very fast. The Pentium was, at the time, a very high performance processor. And the way fdiv was fast, at least in part, was because it did part of its work using table lookups. So there was this table of values stored in the Pentium's hardware. What had happened was, somewhere on the way to fabrication, some of the values had not been loaded correctly into the table. So part of the lookup table, I believe it was 5 entries, contained the wrong results. And for some values of a and b passed to the fdiv instruction, looking up these wrong results in the lookup table would cause it to do the wrong thing. And this wasn't an extremely major error in the sense that it would return 1,000,000 instead of 0, but rather it was often sort of some number of places after the decimal point. The reason that the flaws in fdiv went undetected for some time was that only about 1 in 9 billion randomly selected inputs would actually trigger the bug. And so now the question we need to ask ourselves is, given this relatively low observed failure rate on random inputs, would random testing have been a good way to find the Pentium fdiv bug? And the answer is almost certainly yes. So what we're going to do now is try to figure out about how long it would have taken Intel to find this bug using random testing. And so the first thing we're going to need to do is make an assumption about how many tests per second they can run. And so it's not as if in 1994 they had modern multi-gigahertz hardware available, but rather these Pentiums ran at around 60 megahertz. And so what we're going to say for sake of argument is that it took 10 microseconds to perform an fdiv and verify its result. So in other words, at 60 megahertz, I'm assuming that it would take about 600 cycles to check a particular input for fdiv. So now let's try to work out the math.